Okay, so today we're going to talk about section 3.2, day 2. And I just want to do a quick refresher about what 3.2, day 1 was about. So last class what we talked about was thinking about a curve and knowing that if we knew that the derivative was positive and then all of a sudden became negative, so here our derivative is greater than 0, and here it's less than 0. And that point where it was temporarily equal to 0, that critical value, we labeled that a relative max. So if a critical value occurred when the derivative went from positive to negative, it was a max. And then if your curve then went from negative to positive derivative, then it's going from decreasing to an increasing function, we would have a relative min. And again, that would be at a critical value, an x value that made the derivative either equal to 0 or it could be undefined. Because if my graph went like this, so it still was decreasing and then it was increasing, it could do it at a place where the derivative was undefined. Still a critical value, but it is still a minimum. Whether it goes in a nice gentle turn where my derivative is 0 or a sharp turn where it's undefined, if the direction changes from decreasing to increasing, I'll have a relative minimum. So that's what we were doing last time. And what we're going to talk about today is a different kind of a maximum and a minimum called absolute max and absolute min. And the guidelines for finding those, they're still called extrema, but when we close the interval, what happens is a graph that might have looked like this with a minimum and a maximum, relative minimum, if we close off the interval at a certain place, let's say we close it off here, and we don't look at the rest of the graph, the maximum could occur at an endpoint on my interval. So it doesn't have to be a place where it turns around. If you close the interval, you will have a maximum and a minimum. The minimum here would occur at a relative minimum because it goes back up again. So this would be my relative and my absolute min. This would only be an absolute max, not a relative max, because it's not turning around there. I closed my interval and I don't have a turnaround spot. But this is the max because its function value is highest, and this is the min because its function value is the lowest in the interval that I set. So that's what we're going to do today, is close off the interval and look at maxes and mins a little differently. So the strategy is we need critical numbers. So we still are going to take a derivative, find out where it's equal to 0, where it's undefined, get those critical numbers. But instead of looking at direction changes, we're just going to get function values. We're going to evaluate the function at any critical numbers that we're talking about and at the endpoints. So the A and B, since it's a closed interval, we're going to evaluate at those endpoints. And whichever is the smallest value, we'll call the minimum, and the largest value, we'll call the maximum. So we're not using the derivative to measure direction. We're using the derivative to find critical values in section 3.2, day 2. So what it would look like in number 1 is my step 1 is going to be the same as it was before. Find the derivative. 2x minus 6. My step 2 is going to be the same. I'm going to set that equal to 0 to get my critical value of 3. But now my step 3 is not going to be to draw a number line and look for a change in sign, my step 3 is going to be calculate the function at 0, calculate the function at 3, which is my critical value, and calculate the function at 5. I'm calculating on the endpoints and any critical values that fall within them. And 3 falls within them. So now I am plugging back into my original function, not my derivative. So I'm going to do 0 squared minus 6 times 0 plus 2 and get 2. 3 squared minus 6 times 3 plus 2 and get negative 7. And 5 squared minus 6 times 5 plus 2 and get negative 3. This is my max, my absolute max on this interval. This is my absolute min on the interval. You want to write it as a point, 0, 2, 3, negative 7. This isn't either. So find the critical values, use the ones that are in the interval to get the function value, and then the function values of the endpoints, and then just pick the highest, pick the lowest. That's absolute. Problem number 2, we've got a demand function and a cost function. So the first, and we've also got a limit here on x. So this is my interval that we are talking about, a closed interval for x. So what we're going to do is we're going to write our profit function by first writing our revenue function, which is demand times x. And if I want to write that a little neater, I can use the 20,000 in the denominator, make that a constant multiple, and then I can distribute my x into the parentheses and have 1 over 20,000 and then 60,000x minus x squared. That's a revenue function. And for profit, I want revenue, this function, minus cost. And since I noticed that this is going to have an x term and that as an x term, I'm going to distribute in so that I can subtract my cost away and have a nice profit function. So when I distribute in, I get 3x minus 1 over 20,000 x squared. And then I'm going to subtract my cost, which is 5,000, and 0.56x. I'm subtracting both. So now my profit function, if I write it in order, negative 1 over 20,000 x squared, combine 3x and negative 0.56x, and get 2.44x. And then minus 5,000. There's my profit function. So the next step is I want a sales level that yields a maximum profit. So my step 1 is to calculate the derivative of my profit function, which is negative 1 over 10,000 x plus 2.44. I'm using the simple power rule. In the simple power rule, step 2, I want to set that equal to 0 and solve for x. So I want to know when 1 over 10,000 x equals 2.44, which leads me to x equals 2.44 times 10,000. So I'm going to move my decimal 4 places, and I get 24,400 for my critical value. that critical value is in my interval. So it's a possible maximum, but I need to check whether the endpoints give me a higher profit, because they're also possible maximums, endpoint or critical point. So because I have to evaluate this at 3 different places, I'm going to plug my profit function into my y equals. So right here, I'm going to plug this profit function in. -1 over 20, 1, 2, 3, x squared plus 2.44 x minus 5,000. If you don't have a graphing calculator, you'll have to calculate each of these independently by plugging in your 0 for x, and then your 24,400 for x, and then your 50,000 for x. But graphing calculator will let me go right to my table. And if I start my table set at 0, and I go up by, actually I'm just going to grab my first value, so I'm just going to go up by 1. And my table, when I plug 0 in, is -5,000, which I already knew because these would both be 0. But then I can table set and start at 24,400 and go up by hundreds. And now my table will tell me the profit for 20,400 is 24,768. And then I can do the same thing. I can go either, work my way up to 50,000. That's going to take a while. Or I can table set again and start at 50,000. So that might be faster. And now I got a negative profit, -8,000. So this is definitely the max. That sales level of 24,400 is going to lead me to my maximum profit. So the critical value ended up being something that maximized, and 50,000 is actually going to minimize my profit on that interval. So if I go beyond this production or sales level, I'm not going to be doing a financially positive thing. I'm going to start losing money after this value. All right, moving on to the last question. This is another inversely proportional. So I'm going to create my own demand function instead of them telling me what it is. Demand, which is x, is my equal sign. Inversely proportional leads me to write in a fraction. And cube of the price means I want p cubed down there. And then there's always that constant, a proportionality that I need to figure out. And I can figure that out by looking for the when statement. So I got a little temporary plug-in to figure out k. So it looks like this. When the price is 10, then the units demanded is 64. So the units is my x, the price is my p, and that's going to help me figure out k. K is 64,000. So now here is my demand function. X is 64,000 over p cubed. But they want me to maximize profit. And so what I have to do is rewrite demand as p equals instead of x equals, so that I can get revenue and get profit. So the way we did that was we switched on the diagonal, my x and my p cubed, and then we're going to take the cube root of both sides and get 40 over the cube root of x, which I'm going to write as x to the 1/3. So there's my demand function. I'm going to use it to get my revenue function, which is X times demand. So this is a lot like the extra credit that we did. When you multiply these two together, though, you're going to get 40x to the 2/3 because we're subtracting 3/3 minus 1/3. And that's my revenue function. And then my profit function, I need to take that value and subtract away my cost, which I look back up here, $100 and $4 for every unit. So $4 for every unit and $100. Usually that's the order we do it in. There's my profit function, revenue minus cost. That's what I'm trying to maximize. So my step 1, what's the derivative? It's 80 over 3 x to the negative 1/3 when I subtract 1 minus 4. So now step 2, I need the critical numbers. Well, the easiest way to get the critical numbers is to factor out the lowest degree on x. And while I'm at it, I could factor out the thirds. So this is blast from the past at the beginning of the semester. If I set this equal to 0, I factor out a 1/3 and the lowest degree on x, and I'm left with 80, because I'm factoring out the 1/3 and I'm factoring out the lowest degree on x. And then over here, I needed to think of this as 12/3. So I'll be left with the 12, but I'll be left with x to the 1/3 because it was x to the 0 before, and 0 minus negative 1/3 is positive 1/3. So this is going to help me get my critical values. Here's a critical value, x equals 0. Well, that means I didn't make anything. So that's not going to maximize my profit. That's going to minimize my profit. So I'm not going to worry about that critical number. But this critical number I need to know. So I'm going to set 80 equal to 12x to the 1/3 because I want that factor to be 0. So that means x to the 1/3 is 80 over 12. And that means if I cube this, I can solve for x, but then I had to cube that. So I'm going to get 80, out of here, 80 divided by 12 raised to the 3rd power. I get 296.296. I'm going to round that to 297 because it's a number of units, and I want to make sure that I don't put a decimal point on a number of units. That wouldn't make sense. All right, so now I got to decide, does that maximize profit or not? So they were talking about a price greater than 1. Well, if I look at my demand function, a price greater than 1 would mean that this number is 1 or more. And so the maximum value of x that I could have is, if price is 1, would be 64,000. So I've got a boundary on my x's of 64,000. But this value I have right here is in there. So I'm going to see what happens at 297 units if that maximizes. So if I don't make any units, or I make 297 units, or I go all the way to 64,000, which is my best option? Well, not making any units is going to make my profit negative 100. So that's not good. Making 297 units, I got to plug 297 in here. So I'll do 40 over 297 to the 1/3. minus 4 times 297 minus 100. Let's see what I get. 40 divided by, oops, I'm plugging into my profit function, not the derivative. Start again. 40 times 297 to the 2/3. That's my profit function. 40 times 297 to the 2/3 minus 4 times 297 minus 100. So 40 times 297 raised to the 2/3 minus 4 times 297 minus 100. And I have a profit of $492.59. So what's going to happen at 64,000? That's another question I have to ask, because that's my limiting value. That's my B. I have to check it out. So the easiest way to do that is with my second entry button. And I'm going to change the 297 to 64,000. Now I got to be careful and hit second insert so that I can get those extra 2 zeros there. Same thing here, 64. To get the 2 extra zeros, I need second insert so it doesn't type over. But I'm losing a lot of money there. It's negative $192,100. So I definitely don't want to do that. So my maximizing value was right here. Profit $492.59. So use that to try your WebAssign, and I will see you hopefully on Friday.